Now let's look at the example where omega equals omega naught. So let's take almost the same differential equation, except, sorry, this was u, not u prime. This is the undamped case, so there's no u prime term. And on the right side, instead of last time we had cosine 3t, this time we're going to write cosine 5t. I'm just doing this in example format so that the formulas don't get too ugly. We can do it with numbers, but we're not even actually going to solve this one all the way through. So let's still quickly review. The general solution to the homogeneous case is the same as last time, so I'm just going to write that down. U equals c1 cosine 5t plus c2 sine 5t. If you've forgotten it, you can get it from the characteristic equation of the homogeneous differential equation. This time, when we guess a particular solution to the non-homogeneous case, which is the differential equation we're trying to solve, we try to do the same thing as before. We try to guess a cosine 5t plus b sine 5t, because this side is a cosine, so it's a linear combination of sine and cosine, except these two solutions both already show up in the homogeneous solution. So when we try to put it in the differential equation, we're just going to get 0. We're not going to get cosine 5t. So we need to multiply everything by t. That's what fixes everything in differential equations, apparently. Okay, now unfortunately we've created a product rule, so this is a little bit hard to differentiate, but we will try to do this with no mistakes. No promises. Derivative of t is 1. Derivative of cosine 5t is negative 5 sine 5t. So we get negative 5. This t stays here. Sine 5t. Plus derivative of t is 1. So b sine 5t. And derivative of sine 5t is 5 cosine 5t. We still have a b here. Cosine 5t. Okay, that's one derivative. Nothing to combine or simplify, so unfortunately we get even uglier on the second derivative. This part is nice. It's minus 5a sine 5t. This part needs a product rule, so minus 5a sine 5t, and then this is minus 25at cosine 5t. And then this part's nice again, so this is minus 5b cosine 5t. And then this part needs a product rule, so it's plus 5b, derivative of t is 1, cosine 5t. And then we have a minus 25bt sine of 5t. Hopefully I did that all right. Okay, we need this thing plus 25 of those. Let's see, we can combine these. That's a minus 10a sine 5t. We can combine, I did this wrong. This was a plus. That's why I did that wrong. Okay, I can combine these. This is a plus 10b cosine 5t. And then the 25 times the u of t is actually going to cancel out with these negative terms. So those will go away, which means on the left side I'm just left with 10b cosine 5t minus 10a sine 5t. Everything else is going to cancel once I add in my 25u. And then on my right side, this is cosine 5t. This has to be true for all values of t, meaning we can just compare the coefficients. So 10b on the left equals 1 on the right, and negative 10a on the left equals 0 on the right. There's no sine 5t term. So a is 0, b is 1/10. So our general solution to the non-homogeneous case is, I need to add my particular solution, which I put in a 0 for a and a 1/10 for b, to my general solution to the homogeneous case. So I get u of t equals c1 cosine 5t plus c2 sine 5t plus 1/10 t sine 5t. Okay, so they're all 5t's. This one has a t in front of it. And remember before, a few days ago, maybe a week ago, we used our product sum formulas in a different way, and we were able to write this as a single sine or cosine. We chose to do cosine, because that's what WebAssign in the textbook does. This is cosine 5t minus some angle delta. And then this part is still 1/10 t sine 5t. Okay, so what happens here? Well, this is a regular cosine with some constant, so it's a regular periodic cosine wave. This one has a t in front. So what does this look like? Even if it's 1/10 t, that's fine. It's going to go up slower if it's 1/10, but it'll still go up. I'll just draw it as if it's t. Well, you can just change the scale to do that. And then you see what happens is the sine of 5t gets a lot bigger than usual really fast. Sorry, can't see this. Here we go. Gets a lot bigger than usual really fast. This one stays the same size. This is going to go up and down between c and negative c. So this part of the equation dwarfs this part in the graph. I could add in this and it would look funny. But this part's way bigger. And this is what we call resonance. This was the omega not equals omega part. So we have two things vibrating at the same frequency, and it gets louder and louder. This is, so I don't know if all of you could actually relate to the last example. Maybe you haven't tuned an instrument before, but everyone has held a microphone up to a speaker. And what happens when you try to talk into the microphone, if it's pointed the wrong direction, is you get these high-pitched sounds and they get louder and louder and they're super annoying. That's what this is. This is resonance. That's this part of the solution to the differential equation dwarfing the other part, and you just hear very loud noise.